Right, let's carry on with the next one. The next section is question 15. Question 15 is asking us, describe the tests for, include all chemicals needed and include the chemical reactions for halides such as chlorides, bromides or iodides. Okay, now if you have a look, chlorine, bromine and iodine they're all above each other in the halide, the halogen section at -1 valencies, correct? Okay, and then carbonates and sulfates. Essentially the tests break down to a flowchart pretty much like this, okay? Well, we've got to test and they want to know if there's a halide involved, right? In both cases common, we're going to add an acid, okay? If there's an acid added, we look and see if there's bubbles of gas. That means we've got a carbonate involved somewhere, all right? Because when you put an acid and a carbonate, you get CO2. So let's have a look here, all right? So first of all, let's say we've got the test over here and we suspect a halide, all right? So what do we do first? Now, first thing is we add in AgNO3, silver nitrate, right? Silver nitrate, AgNO3, we add to our test tube. All right? Now, if we add silver nitrate to it, right? If there's a halide present in here, the silver nitrate, right, is going to link up with one of the halides. The silver is going to link up. In this format, when we put the silver nitrate, remember this is soluble, isn't it? But if you go back to your solubility tables, silver plus any of the halides, that's insoluble in water. So if there's a halide, we're going to have Ag plus NO3, and I'm going to put that as aqueous and aqueous. They are now dissolved, right? Plus, let's say we have a suspected halide. This halide is going to be in solution as a -1, isn't it? Because it's in the test tube. So it's something in that water already dissolved. So it's going to be there. Now, do you recall what we said is that if we had that silver plus any halide, it's not soluble, is it? So what do we have to do? Well, straightforward, we say, we are going to give us a precipitation reaction, correct? It's going to give us a precipitation reaction. Quite simple. It comes out as a powder in solution because it's not soluble. So therefore what happens is the silver goes and you get the silver halide precipitate. Okay? So first of all, we've got a solution. We've added a silver nitrate to it, and that's going to, if you get a precipitation reaction, okay, then you know that the chances are there's a halide in there. But we still have to test. Okay? Let's have a look at what we could have. Let's just put the equations down. Ag plus NO3 minus, over there, all in aqueous. And let's say we have a Cl minus, that goes to AgCl, solid, plus NO3 minus. Okay, instead of writing out every single time, Ag, etc., I'm just going to put plus over this side. Let's just put this one in red. Plus, for example, a bromide gives us AgBr, solid, plus NO3 minus, right? And lastly, right, we can put in here, let's use the green one, plus an iodide, I minus, goes to AgI, solid. and essentially all of the above here, these are all going to precipitate. Okay, I forgot the NO3. Okay, plus NO3 minus. All right. So in all the cases there, you're going to get a precipitate coming out. So the chances are that it's a halide, okay, because this is the halide test. We're not totally sure yet. Okay, we're still going to add something else. But before we do, okay, let's just look here and we say, all right, let's just say here we've got, if it's white, the chances are it's a chloride. If it's pale yellow, the chances are it's a bromide. And if it's dark yellow, it's an iodide. Okay? A deep yellow is an iodide, a pale yellow is a bromide, and a white precipitate is a chloride. The next step that we do, okay, in this process is we add HNO3. This is what? Nitric acid, right? We add nitric acid, okay? Why? Because we want to make sure that it's the halides. Because if it was a carbonate, it would bubble off. Okay, we'd get CO2 coming off. So we add that. Now, basically, if no gas given off, then you have the halides. Whoops. You have the halides over there. Because when we add the acid's going to react with that powder at the bottom, isn't it? So if it's a carbonate, it's going to dissolve it and it's going to bubble off. Because basically, none of these are soluble. These are not soluble in HNO3. All right? Now, that's the test for the halides, right? Then let's have a look. What is the test for a carbonate or a sulfate? Well, carbonate or a sulfate. Right, what do? We add BaNO3. BaNO3 to the mix, barium nitrate. Okay, let's just put it here. Not mitrate, barium nitrate to the mix. All right, what's it going to happen? Well, essentially, the barium nitrate, okay, is soluble. But when we add it to a mixture containing carbonates or sulfates, it's going to change as follows. You're going to have barium plus 2 NO3 minuses, all aqueous, right? Like so. And if we have got, let me just put it here. If we have got in here I want to just change it. If we have got in here a sulfate or a carbonate, okay, one of those two is in here as well, all right? Essentially, what is going to happen is we're going to have an ion exchange, we're going to have a precipitate again. So we're going to have sulfate, okay, coming out, all right? Or we're going to have Ba carbonate coming out, right? Like that. And we're going to have our 2 NO3s there and plus 2 NO3 there. And this is going to be a solid and that's going to be a solid. So essentially at the bottom of the beaker, all right, we are going to have a precipitate sitting there, okay? Well, the next step is we now add HNO3 again. Right? Now, if we add HNO3, Okay? You look for two things. One, bubbles or no bubbles. If there's no bubbles, then it's a sulfate. Because, once again, barium sulfate is not soluble in HNO3. But if you get bubbles, it means you've had an acid plus a carbonate, which means you've had HNO3 aqueous plus the carbonate is BaCO3, isn't it? And what are we going to get? You're going to get barium nitrate coming off, all right? You're going to get BaNO3 2Y plus 2 minus 1, remember that? Always have to go back to that, plus CO2 plus H2O, all right? That's what you get. It's a standard acid carbonate reaction. And the CO2 is the bubbles, right? So the acid and the carbonate, all right, are going to react. And on the other side, if it's a sulfate, it's not going to react. So remember, the key of this is the HNO3. Now, in many cases, you could be asked to do it backwards, all right? Where they give you unknowns in jars or whatever, all right? And they want to give you what tests do you do to find out what they are. All you've got to do is go through these tests backwards, for example, right? So you'd say, right, if I add the acid and I get bubbles, it means I must have had a carbonate in there. If I get the acid and there's no bubbles, then it means I could have a sulfate or a halide. Then we would go and we'd add the silver nitrate to get a precipitate of the halide. And we'd look at the color of that, correct? To see which one it is. Just let's think about that again. If we've got an unknown and we add a drop of HNO3 and we get gas, all right? Let's just for example, just do it. I know it's not part of the question, but let's just expand upon it a bit. If we add to an unknown, okay, and we've got, let's say we've got a precipitate in there, and we add a few drops, HNO3, okay, and we get bubbles. Then bubbles, then it was a carbonate. But if we get no bubbles, then it means it was either a sulfate or a halide. Correct? The next thing is then you add, okay, now we say, okay, we add AgNO3, correct? From our other thing there, we add silver nitrate. We add silver nitrate to it, and if we then get, okay, a precipitate, all right, out of that, we know we've got a halide involved there, right? Okay, so these are other ways of looking at it. Just remember the HNO3 tells us the carbonate or sulfate, or it could have been a halide, right? Which means that what we do is if we get a sulfate or a halide, we add AgNO3, okay, at the top end, and what do we get? We then look at the precipitate over here, and we check and see the color. Okay, right, let's move on to the next question, okay? And here they say, discuss the 4 driving forces behind chemical reactions and use a chemical reaction to illustrate each one independently. Okay. Well, first of all, what are the 4 driving forces behind the chemical reactions? Let's have a look. Okay, let's have a look here at, first of all, shall we just put in here the question number? This is question 16, right? Question 16. Well, we've got 4 reactions. First of all, number 1, we've got precipitation. Number 2, we've got gas forming. Number 3, we've got acid base. Okay, all right. And number 1, all of these here are essentially ion exchange. We'll go into that when we look at the chemical reactions, but it's in essence that the anion and the cation exchange basically partners. Okay, the cation goes off with the new anion and vice versa. Okay, the last one is then number 4 is redox, which is electron transfer, correct? Electron transfer reactions. Okay, let's have a look at a precipitation reaction. All right, any one of the previous we could have used. This is PPT, precipitation reaction. I've just said AgNO3, okay, aqueous plus NaCl, aqueous goes to what? AgCl solid, right? All right, and AgCl, hang on, remember you got to check, +1, yeah, it works, plus NaNO3, sodium nitrate, okay? And this remains as aqueous. Now the ion exchange, let's just have a look what we were talking about. Let's just split up this one first. When it went into water, the dissolution was Ag +1 plus NO3 -1, remember? And on this side, we had here Na +1 plus Cl -1, right? And what happened is this one went off with that one, changed, and this one changed partners like that, correct? That's what actually happened. This is the ion exchange. The anion and the cation, the anion is another negative ion, it's the negative one. So this is the anion and the anion, this is the this is the cation, and they exchanged positions, they exchanged partners, like a dance. They did that whole thing of cutting in on people and exchanged partners in essence. Right. Now, let's move up and have a look at the gas forming. Well, we've just spoken about the gas forming ones, but a standard reaction is a carbonate, isn't it? Okay, I've done here calcium carbonate plus HCl, CaCO3 plus HCl. And what happens here? Acid carbonate means we get an acid salt, CaCl, but I must balance, +2 -1, so we need a 2 there, correct? Then that's going to go to CO2 plus H2O, all right? And then we can go balance it from there, because let's have a look and see once again. Ca +2 plus CO3, all right? Which is a -2. And an H plus a CHCl minus. I know that H plus is actually an H3O plus. I'm only using it here just so that we can keep it simple. Okay, and what happened? We had our transfer, didn't we? Calcium went to the chloride, and the CO2 came from here and the water. These guys over here, okay, they did their thing, giving us those 2 pieces there, right? All right, and that's a standard reaction that we get, all right? The next reaction is the acid and the base reaction, a neutralization reaction. All right, I used NaOH plus aqueous. I actually should say aqueous in all cases, hey? All right, aqueous in all cases, and we get plus HCl, goes across to NaCl plus H2O. All right? And then you can go balance it. But essentially what happens is, let's have a look again. There we go. This is Na plus OH minus plus H plus Cl minus, right? And what did we do? Can you see again, we had the ion exchange. This guy, okay, went with that one, positive to the negative, and these two got together to form water, right? The last one is number 4, and number 4 is in essence our electron transfer reaction, okay? And in the redox, I use copper sulfate, okay? The one you're going to see often. I said we've got copper sulfate aqueous plus Zn solid. And what happens? This reaction is a what? It's a displacement. Remember from last year? Okay? And when you, or even the year before, when you did the whole thing of copper sulfate dissolved in water and we put a piece of zinc in, what happened? Well, the copper flaked out, precipitated, and the zinc dissolved. What actually happens? This is in solution. Remember, copper plus 2 plus the SO4 minus 2. And we come along and we add a zinc solid in there. Okay? Now, guys, what happens is the zinc was a solid, the zinc melted, and the copper, okay, the zinc melted and it became zinc sulfate because we got copper, okay, not going to do it with an eraser, Cu as a solid. Let's have a look what happened across this boundary here. The zinc was a solid. It dissolved. It dissolved. It went into solution as Zn plus 2. How do we know this? Well, we know it because the copper was a plus 2, and all of a sudden copper is now a solid. It's physically there. It actually happened. So what did we do? How did this happen? Well, there must have been 2 electrons got added to that to make it a solid. Because remember, it's an element now. It was an ion of a plus 2. We cancelled out the plus 2. How did we do that? We added 2 electrons to it in order to cancel out the plus 2. That's the only way you're going to do this, okay? And it became that. Therefore, this must have given off 2 electrons, didn't it? Now remember, oil, rig, okay? Oxidation is loss, reduction is gain. Can you see? I shouldn't have put that there. I'm in my own path, but be that as it may, okay? Let me just put it in over here, and I'll put it in red. Okay, oil rig, which one gained? The copper ion gained 2 electrons. So this is reduction is gain. This is reduction. This one must then be oxidation. Right? Hence redox, reduction, oxidation. And you always get them in a pair. Okay? So that is showing the other driving force behind this process, isn't it? Okay? Now, let's just have a look at the next one. All right? They are saying to us here, let's have a look at the next question. All right? And the next question is related to discuss factors affecting conductivity in an aqueous solution. What do they mean? They're simple. What they actually mean is they're saying, and this is number question 17, if we have got a beaker full of stuff, dissolved stuff, okay, we got a beaker with dissolved stuff, and we go and put 2 electrodes in here, and we join them up with a battery, okay, and we notice current flowing. Okay? Current flowing. How do we measure current? Simple. We go along and put an ammeter in on that side, don't we? And we say, right, the electrons are flowing, aren't they? Because this is the negative side, so I've got lots of negatives here, plenty of positives here, and essentially this flows through here, doesn't it? It needs ions, because the ions are going to conduct it, aren't they? And this is our electrolyte, isn't it? Okay? It's our electrolyte. It's conducting electricity. But now you can either have the ammeter going, maybe no current flowing. In other words, very little, very few electrons are actually going across here, all right? Because actually the ions are what's going to do the transfer. So there's not many going across. Or it can go boop, and an electric current just starts flowing through it, right? The conductivity is a measure of how much that ammeter is going to move, how much electricity can get through, and in other words, how many electrons, because the flow of current is the flow of electric charges, right? All right, so now let's have a look then. First of all, okay, it must depend upon what? Number one is the concentration. Okay, more ions, more current. Correct? More ion, more current. All right? In other words, if you've got a lot of ions dissolved, okay, it means that there's going to be plenty of ions that can flow, therefore the current is going to be strong, flowing through there. Remember, pure water does not conduct electricity. We had to add a drop of acid to make it actually work, didn't we? Okay, then the second part is the type of substance. Okay, in other words, the type of electrolyte. Strong, weak, or non-electrolyte. A strong electrolyte, okay, highly soluble. Not highly soluble. Okay, not insoluble, but not highly soluble. Non-electrolyte is stuff that is insoluble in water. Okay, insoluble, right? Now, why? Oh, by the way, these non-electrolytes, okay, now let's just leave that for the time being. All right, so we've got, in other words, a strong electrolyte, table salt. If you put table salt in water, you can dissolve loads in there, can't you? Right? It's highly soluble, and you get lots of ions coming into the water. Okay? The next statement is number 3 is going to be temperature. All right? That's just the way to think about it. Strong is, for example, salt, okay? Sodium chloride, potassium nitrate, KNO3. Weak is, for example, acetic acid. Okay? Things like acetic acids, vinegar, citric acid, lemon juice, things like that. They're very weak, okay? But they'll just take a few electrons across, not a lot, all right? Insoluble is things like, for example, oil. Okay? Oil doesn't dissolve in water, does it? It doesn't mix with water at all. Okay, it does. You can get an emulsion of the two mixed up together. If you put salad dressing, right? You put vinegars and vinegar and oils together, they separate, don't they? Remember we spoke about that in the whole thing of mixtures and stuff? They separate out and you get the different layers. But if you shake them or blitz them with something, they mix up to form like emulsions and stuff. Temperature, okay? The higher, the more conductive. Okay? The higher, the more conductive. Okay? In other words, that's that. So, yeah, essentially, that's the discussion on the electrolytes and the movement of current through an electrolyte. Okay, thanks. I've managed to get that one bang on time. Thanks for watching. The next one we're going to start, and these are the ones where we're going to start looking at molar masses. We're going to start looking at the at molarity. We're going to look at concentrations, and we're going to get going from question 18. Thanks. Cheers. Hope this is really going down well, and you guys are working these through with me. Remember, it doesn't help not to, hey? And if you're stuck, go back to the textbook on the theory and just go and have a good look at it. Okay, cheers. I'll see you in the next one. Bye.